Okay. So I just wanted to spend some time with the current numericals. We discussed those very quickly in the online class. I just also wanted to go through each of them in a little bit more detail. Okay. So I'm not going to write each problem. We will just solve it in the same order in which the sheet has them. So we will save some time that way, and we will just look at the numericals in terms of the calculations, in terms of the equations, etc. The actual calculations you can do on your own after that. Okay. So we'll start with the first one. Nmos Okay, so actually this is a numerical where they are telling you to plot the VI characteristics for different families, that is for different levels of VGS. So basically you will get a family of curves, and each of those curves will be for one value of VGS. So we will start with VGS equal to 1 volt, and VDS, let's say it goes from 0, 1, 2. So power supply, let's say, is 2 volts, even though the problem says 5 volts. We will not go all the way up to 5 volts. Okay. And another thing is this number, many of you asked this also. This number is, maybe in some problems it might be useful, but it is just there for the sake of completion, because it's always important to know what technology, what process we are working with. So that is why that number is there. Sometimes not too many problems, but there might be some numerical where we will use that number, but otherwise the actual number, that is the technology node or the channel length, directly we will not use. And another question that many of you asked, this number in terms of our layout design rules also, that number is 2 lambda, that is 0.6 micrometer is equal to 2 lambda. Okay, so let's look at this first one. Basically I just want to explain the approach, that is how we approach these current calculation problems. So this one is very direct. Okay, we just have all the numbers, we just want to plot it. And always for current calculation problem, okay, there are certain parameters, that is k, n, okay, so two different variables, and there is a slight difference between the two. The first one we have seen beta, also it is called as Kn, and it is the product of mobility oxide capacitance per unit area multiplied by the transistor W by L. The second one is Kn prime, which is just mobility into oxide capacitance. This is constant for all the transistors in a particular technology. That is, mobility hardly it can change. It cannot change when you fix a particular substrate with certain amount of doping level. The mobility is fixed. Okay, and similarly, C oxide, as we will see in the numericals, C oxide has a calculation, but this, okay, is constant for all the Nmos transistors because there is a Kn here. Mu n, mu p, mobility of electrons and holes are slightly different from each other. So that way there will be one number for electrons, one number for holes. But the Kn prime or Kp prime, that is the same for all the transistors, because for all the transistors we know that the only thing that we can change easily, threshold voltage also we can change, but those are special cases. The general case is the W by L. Okay, so W by L can be changed. So this part remains constant. When you multiply it by W by L, you get Kn or beta. Okay, so what I would recommend is for all the numericals, okay, calculate this. This is a one-time task. We can reuse this irrespective of whether the current is in saturation or in linear. Okay, so let us first calculate that term. So we have C oxide equal to, okay, this also, the general expression for capacitance that we know is A epsilon naught by D. But in this case, the A will not be used because the oxide capacitance inside the current equation, when we were doing the derivation, the A came into the picture, but then we substituted A with W into L and got the final expression for current. So when we talk about the C oxide, it has units farads per centimeter square. So don't add the area of cross section. Sometimes you might not have it, sometimes you might have it, but either case, do not add that in the C oxide calculation. That is the first thing to remember. Okay. The second thing, equal to, and almost always our tin oxide between the gate and the substrate is going to be silicon dioxide, and silicon dioxide is having a relative permittivity of 3.9 into epsilon naught is 8.85, and for our usage E minus 14, okay, because it is in centimeters, and divided by oxide thickness, that is given 100 into E minus 8. Angstrom is actually 10 power minus 10 meters, but we will use the number in centimeters. So 10 power minus 8 centimeters. So this will give me the oxide capacitance. Okay. And once I have the oxide capacitance, let's see if I can calculate this. Okay, so 3.45 into e power minus 7. So sorry, 34.5 into e power minus 6. And this is the oxide capacitance. When you multiply this with the W by L and the mobility, you will get beta. So therefore, for this whole transistor, therefore, beta equal to, okay, so 34.51 into 350, 34.51 10 power minus 6 into 350 into 350 is in centimeters square, so don't have to do anything there. Okay, we want it in centimeters, into W by L. Okay, so I think I might be wrong. E minus 2 is what I'm getting, and this is the beta. Okay, and what is the units for this constant? This is the physical constant. Definitely it has some units. Directly we can calculate the units by multiplying the units of the individual terms, farads per centimeter square, multiplied by centimeter square per volt second, multiplied by W by L. But another way to do it is rearrange. If you see the current equation, current equal to beta into voltage square. So the units of beta must automatically be amperes per volt squared, because when you multiply it with the volt square, they will both get cancelled, you will get amperes. So that is the value of beta. So let us start with the first this thing. So I want the value of current. Okay, so start with the first value, VDS, VGS. So always we check two things. One is if the transistor is on or off. So in this case, VGS is 1 volt. This is the Nmos transistor. VGS is greater than 0.7 volts. So the transistor is on. Okay, and once it is on, we have to check whether it's in linear or saturation. So in that case, we will be able to decide what is the current equation based on the mode of operation of the transistor. So in this case, VDS equal to 0 volts. So the condition, I'll write the conditions here. Okay, VGS greater than VT. This is the first question mark. The second question mark is VGS minus VT greater than VDS. Okay, so the two things to check. These are the two things that we have to check. So first we have already checked that one, so that seems okay. So it is on. The second one, VGS minus VT. So in this case, 1 minus 0.7 is 0.3. 0.3 is greater than VDS, which means it is in linear mode of operation. Linear, I will write that. Okay, and since it is in linear mode of operation, we have the equation for current, which is beta into VGS minus VT minus VDS by 2, the whole into VDS. This is the current equation. Okay, but since VDS is 0, the whole thing will become 0. So I 0 amperes. In this course, we don't care about the calculation. We know that there are certain currents flowing all the time called as leakage currents, because we have discussed all these non-ideal effects. There is subthreshold conduction also, but we are not going to calculate all those currents. Okay, if we find out that the transistor is off, current equal to 0. If VDS equal to 0, then also current equal to 0. Okay. So one question that you might ask me is VDS equal to 0, and if it is in saturation mode, then we will still get a current, right? Because saturation current, the expression is beta by 2 into VGS minus VT the whole squared. VDS is not there in that equation. So even if VDS is 0, we will get a current. But here, since VDS is there in the equation, VDS equal to 0 means current equal to 0. But saturation, okay, the thing to remember is, if VDS equal to 0, you will never satisfy this condition. Okay, so you can never have VDS equal to 0 and the current and the transistor in saturation mode. So the condition will never come. So we don't have to worry about that. Okay, so this is the first case. Second case, excuse me. Second case, VDS equal to 1. Okay, and here definitely current will flow. We have to use this equation, and this is why that beta is very useful. We have almost everything. I just have to calculate the second part, and let me just make sure it is still in such a linear mode. So VGS minus VT, VGS minus VT is 1 minus 0.7 is 0.3. 0.3 is not greater than 0.3 and 1 volt. So definitely 0.3 is lesser, which means it is in saturation mode. So in saturation mode, the current equation is, I will write that here, saturation beta by 2 into equal to, so very easily I can write 2.41 E minus 2 divided by 2 into VGS minus VT the whole square, 0. Okay, so 2.1 21.74 milliamperes. Okay, that is the current. And the next case, it's very easy for me because the transistor continues to be in saturation. VDS has increased. Okay, as VDS is increasing, it can never go from saturation back to linear. The one side is linear, the everything else is saturation. So for the third case, okay, I don't have to calculate this again. I know it is saturation. Our equation says that the current is going to be the same. It is the same value. So directly I can write that 21.74 milliamperes. Okay, so very simple. So we will plot this, I'll remove all this here, and we will plot this one value. Okay, so the second case we will try for VGS equal to 2 volts. Okay, so start with the first case. VDS is 0, don't have to worry about anything. Okay, so this point is the starting point for all values of gate voltage. Any value of gate voltage, it is going to be 0. Okay, so let us try for the second one. In this case, condition VGS minus VT, 2 minus 0.7 is 1.3, 1.3 is greater, so it is in the linear region. And now we have to calculate 2.41 E minus 2. This is my beta multiplied by VGS minus VT, 2 minus 0.7 minus 1 by 2, the whole into 1. So this is equal to 2.41 into 2 minus 0.7 is 1.3. 1.3 minus half is 0.8. 1.928 or 19.28 milliamperes. Okay, and the next case we have 2 volts for VDS, and now if you compare 1.3 and 2, it would have gone into saturation. So therefore the current is 2.41 by 2 e power minus 2 into VGS minus VT the whole squared. So 1.3 the whole squared. So it's coming 20.36. Okay, so this is the second value and it will continue for different values of VGS. This will be the same current because it is gone into the saturation region of operation. Okay, so just check the calculations again. I'm not very convinced because I don't have a good calculator. Okay, let us look at the third problem. The second problem is identical to the first one. Actually, it has even fewer cases. So let us go to the third problem. Nmos enhancement transistors has the following properties. Okay, Vt. So just one second, I realized there is an extra word there. Nmos enhancement transistor. Okay, Nmos. So we have been looking at only one NMOS. We have a source and a drain, okay, and the channel is induced by the gate voltage. Then the source and drain are connected. There is another type of NMOS which is called as a depletion NMOS. So the depletion NMOS is slightly different because in that particular transistor, it's a completely different looking transistor. The channel region is also fabricated along with the source and drain. Okay, the channel region is also fabricated. Then how do you turn on or turn off the transistor? So in that case, NMOS depletion transistor on for because the channel is already there. We don't need the gate voltage to attract any electrons and form the channel. The channel is always there. So even if I don't apply a gate voltage, the transistor is on. So then how do you turn off the transistor? You turn off the transistor by applying a negative voltage. Okay, you apply a negative voltage and all the electrons get pushed away. Okay, and you get a depletion region and then the transistor is considered off. So that is the way the depletion region or the depletion NMOS depletion transistor works. We are not too interested in that particular transistor. It was useful before when certain functionalities were required. We will see that briefly when we come to a logic family called as pseudo NMOS, but for now don't worry about that. NMOS enhancement transistor, which is what it says in the numerical, is just our regular NMOS transistor. Okay, so Vt equal to 0.8. Now we see Kn prime. Okay, Kn prime equal to 20. Okay, and Vg okay, and in this case they have given you id equal to There's a small misprint in the sheet. ID is not 0.24 amperes, it's 0.24 milliamperes. Okay, so please make the correction. ID equal to 0.24 milliamperes, and they are asking you what is the W by L of the transistor. So we have to look at the operation and find out what is the region of operation. Linear, it's definitely on because it's quite a big current, 0.24 milliamperes through a single transistor. Okay, so once we find out what is the region of operation, then we have the equation. So from that equation, we have the left hand side. Generally, we are trying to find out the current. This time we have the current. We have to solve for the W by L. So we will find out the region of operation. We have these terminal voltages. VG and VD are given, but since Vs is 0, we can take them as VGS and VDS. So first, Vg is greater than Vt, so definitely it is on. From this number also we can see that. But in addition, is it in linear or saturation? That is the question. Clearly Vds is higher. So whenever Vds is higher, okay, you have to remember automatically that means that the transistor might be more in saturation. So here also Vds is greater than Vgs minus Vt, which is 5 versus 2. So the transistor is in saturation. Okay, so then write down the current. We have 0.24 into 10 power minus 3 equal to, now Kn prime. So again recall, Kn prime is equal to mu n into C oxide. Okay, so that is given to you here. Mu n into C oxide 20 into micro, so 10 power minus 6 into W by L, okay, divided by 2. This is the equation. The whole into VGS 2.8 minus the whole square. So this is the equation that I can use, and directly if you solve for W by L, I think you should get 6. So we did this in the online class also, but there we forgot to make the correction for the current. So instead of milliamperes, we used amperes. So instead of 6, we got 6,000. 6,000 is a very, very large number for W by L. It might not always be possible also because there's a upper limit on the W for any technology. So 6 is a more realistic number. Okay, so W by L equal to 6. And the second part is quite easy. They're just asking you to calculate the current. So this time we can use this W by L. W by L, once it is set for a transistor, you cannot change it. We can change it during the design stage, but once we have a transistor with a current flowing through it and the W by L is calculated, every time we calculate, we have to use the same W by L only. So we can reuse this number 6 and calculate the current in the second part. Okay. Okay, so now a Pmos transistor is exactly the same as Nmos transistor in terms of the properties, etc. But because the charge carriers are holes, okay, the conditions become exactly opposite. It's like multiplying some set of conditions with -1. So when you multiply a set of inequalities with -1, the direction of the inequality also will reverse. That is one of the properties of the negative numbers. So the same reason why all the conditions are also opposite for the Pmos transistor. Okay. So let us do this one Pmos transistor. Pmos transistor. Okay, so there are other things, but we will look at this part first. And it's very easy. It's just that they're asking you the oxide thickness. So if we calculate that, okay, 1.33 into 10 power minus 3 equal to T oxide equal to, just rearrange that. Let's see what we get. No, that's wrong. So let's just leave it. Let's not get confused. Uh, so this answer will directly be in centimeters because the capacitance is in farads per centimeter square, and the epsilon we have used 10 power minus 14 is in centimeters. So when we cross multiply, we will get the answer in centimeters. You can leave it. You don't have to convert to angstrom or anything like that. 25.9 into 10 power minus 11. Let me just check that. 3.9, 8.85. That gave me 25.9 minus 14 minus 3 minus 11. Okay. So this is the oxide thickness. And fortunately, we don't have to use this directly. They're just asking for it. We can use C oxide directly. That number is already there. Okay. So let us continue with this calculation. And VTP. Okay. So remember VTP for a PMOS transistor is a negative number. Okay, so negative number means that the number, when you're using this in any of the calculations, you have to use the number along with the sign. Okay, don't just take the plus 0.6 part. You have to put it as minus 0.6. Okay. Okay, so first scope of confusion, first level of confusion, VSD, VSG. These are not variables that we use anywhere in the equation. Okay, the variables that we use are VDS and VGS. So from network analysis, VDS is nothing but VD minus VS. Same way VSD is VS minus VD. So to go from one to another, I have to okay, first I have to get these variables. We cannot use those variables at all, the first set that is given. Okay, so get it in terms of the variables that we use, and then we can go for the calculations. So they want the current, obviously. So first VGS is minus 1 volt, VGS minus 1 compared with VT, which is greater. VGS is minus 1, VT is minus 0.6. Okay, so this means that the transistor is on because the conditions are reversed for a PMOS transistor. Okay, VGS is lesser means the transistor is on. So next we have to see linear or saturation. So for that, VGS minus 1 minus of minus 0.6 versus minus 2, and minus 1 plus 0.6 is minus 0.4. So VGS minus VT is greater than VDS. This means that it is in saturation. Okay, the condition for saturation and linear are reversed. But once we find out it is in saturation, then directly use the saturation current equation. Saturation current equation doesn't change. Okay, it is always beta divided by 2 into VGS minus VT the whole square. So therefore here I can write it here maybe. So therefore IDS equal to beta is 30 into W by L. So that is 3, okay, 1.5 divided by 0.5 divided by 2, sorry, this is microampere, so 10 power minus 6, and VGS minus VT the whole square. So minus 1 minus of minus 0.6, which is okay. So just finish the calculation, we'll get the value for current. So few things to remember. First obviously is that all the current equations are reversed compared to the Nmos transistor. And second important thing is, the once you determine the region of operation, then the current equation stays the same, linear or saturation. Okay, if you change both, that will be a mistake. So make sure that you are calculating this properly, then use the saturation or linear current equation. They are the same for Nmos and Pmos. Okay, and everything else is the same as before. Okay, so the next two problems are quite direct. I will not solve them. We already discussed them in the class. The last problem we have not discussed, and this problem is the most recent, just finished supplementary semester exam, where I was the teacher there also. There this problem had come, and it's a very, I wouldn't say it's a direct problem. Okay, so let me just write down the problem also. Nmos enhancement transistor has the following parameters: Vt equal to Okay, so this is the general this thing of the problem. They have given the some parameters with respect to the transistor: threshold voltage, oxide thickness, and mobility. And they are giving the gate voltage is 1 volt. Okay, we don't know what is power supply, etc. We only know that gate voltage is 1 volt. And they're giving the current. So this is somewhat similar to one of the numericals that we did, but now they're asking you to find out VDS. Okay, so how do we find out what is the drain source voltage? Without knowing the drain source voltage, we don't know whether it's in linear or saturation also. So we don't know which current equation to use. So what I would do in this particular problem is you take one value of VDS, choose one value, okay? You assume that it is also 1 volt because VG is 1 volt, okay? Calculate and see what you are getting, and then maybe we can determine whether it is above or below this number. So let us do that, okay? Let us assume VDS equal to 1 volt. Okay, then automatically the transistor is in saturation, and we have the current equation which is equal to, so I have to calculate C oxide also. So C oxide will be 3.9, 8.85 E minus 14 divided by 10 into E minus 8 equal to. Okay, so 3.9, 8.85 divided by 10, that is 3.41, and 14 and 8, I'm getting E minus 6 farads per centimeter square. So I have to use that 3.415 into 10 power minus 6 into W by L is not given. I don't know what is the W by L, so let us just assume it is 1. Okay, the whole thing divided by 2 into, what is this suddenly, 0.3? Sorry, what is this? Is not 0.3, 0.7 the whole squared. What is 0.7 the whole squared? It is saturation current equation, VGS minus VT the whole square. So if you evaluate this, what are we getting? Okay, so this is the problem. How are we going to ever get 50 microamperes? And the problem with this is we don't have W by L. So right now we are getting this number, but we are using a very low value of W by L. W by L equal to 1. So now what we have to do is we have to assume a much higher value of W by L. Let us assume W by L equal to, say, 100. Okay, 100 is a very big number, but it is possible. It is possible to have W by L equal to 100. And let us calculate for the same one. For W by L equal to 100, okay, so W by L equal to 100, it just 83 microampere. So now we have found out that the constant value is 83. It is higher than 50. So once I have set this, then I can try to use saturation because, sorry, linear, because this is in saturation. In saturation, whatever value of VDS, it will be 83 only. So now I have to go back to the linear equation, use W by L equal to 100 and find out what is the VDS. So that is just a backward this thing. That is somewhat simpler, but still you will end up with a quadratic in VDS and you have to solve that for VDS. So that's why I said it was quite a complicated numerical. And once once you finish that, there's also a second part for IDS equal to 125 microamperes. So now definitely we cannot get 125 because the maximum value is this one, 83 microamperes for saturation. So how do we get 125? For that we have to use the equation for channel length modulation. So we have to assume a value for lambda and then we have to solve for the VDS, which will give us 125 microamperes. So that's why problem is quite complicated, but still the way to work with all these problems is whatever numbers you don't have, try to assume them such that it is close to what we require. Okay. So we will stop here with the current calculation. We have done many so far, so I think this should be enough. Okay, so we will continue with our unit 2 topic, which is inverter. Okay, so inverter VTC, we have done the detailed analysis, regions A through E, why they are divided into 5 regions, etc. All those explanations we have discussed. I'll just do a little bit of like a self test. Okay, so I'll draw some VTCs. Okay, so ideal, this we have seen. Okay, our transistors can not operate like this because this means that there is a sudden transition between the on and off. But as we know, there is a region where both Nmos and Pmos are conducting. So we will never get this type of operation. This is purely the ideal case. Okay, ideal case can never happen at the transistor level, and this is basically our digital assumption where everything is square wave. So this is okay, but let us look at these three. These three we can get. Okay, can you rank them in order of let's say in terms of, we can rank them in many ways. So which is the best and which is the worst in terms of power consumption? So let's rank on top in terms of power, okay, and bottom in terms of, or let's not do the other one now because we've not yet discussed noise immunity in these lectures. So first let's look at power consumption. Power consumption, very important. We've discussed this many times, but still I will mention it again. Okay, in this case power consumption is 0 during the operation. Okay, because the switching happens instantaneously, but in the real cases switching doesn't happen instantaneously. Here maybe a small region as long as the voltage is constant, and here, okay, there is no power consumption. Why there is no power consumption? Because in this small region and this small region, okay, one of the transistors is off, and if one of the transistors is off, current cannot flow in that circuit because there are only 2 transistors in series. If one is open circuit, current cannot flow. So here and here is fine, but the middle part, okay, this is the place where the power is being consumed because both transistors are on. and because this region is very large, okay, as long as this is there, that is for a very high range of the input voltage. What does this mean, this region is large? This means that, say, this might be 0.2, this might be 1.8, okay. So for this whole range of voltages from 0.2 to 1.8, that is when the input is changing from 0.2 to 1.8, or from 1.8 to 0.2 also, both ways, okay, the power is going to be consumed, and that's very bad because this region in which 0.2 to 0.8 is quite large. It's almost the whole rise time of the signal, right? And the opposite is also true. So this is the third place, definitely. And by the same logic, if you compare these two, this is first place, this is not so good, but it is okay, okay. So it gets second place. So this is the analysis in terms of power. Now another thing I wanted to share, and this will naturally lead into our discussion of noise immunity. Okay, so what is this third waveform? First and second, they are reaching zero level in the x-axis. This one is not reaching the zero level. Why? Okay, and what is the effect of that? What is the effect of that particular phenomenon? So that we will discuss in the next topic, which is what is the meaning of this noise immunity.